Examine a raw micro-CT cross-section of a Herculaneum scroll. It is a dense, noisy, three-dimensional voxel grid. Beside it is the output of the EduSlab pipeline, sharply defined, highly legible Greek characters extracted from the ancient text known as P. Herc 1667. This extraction does not rely on optical character recognition. There are no generative language models guessing the missing letters, and no paleographers drawing lines where they think ink should be. The artificial intelligence producing this output performs a strictly binary pixel-by-pixel classification. It looks at a microscopic 3D region of the scan and evaluates it simply as ink or not ink. The difficulty lies in the chemistry. The scribes of Herculaneum used a carbon-based soot ink to write on a carbon-based papyrus substrate. When scanned with X-ray computed tomography, the ink and the paper exhibit nearly identical density. There is zero visual contrast in the raw data. The inability of human experts to see and label carbon ink created a data bottleneck, stalling the training process, regardless of the neural network's design. Supervised machine learning operates on a core rule. An algorithm cannot learn to identify a pattern without a labeled ground truth dataset to study. Researchers had access to physical scroll fragments that broke off during historical unwrapping attempts. These fragments had visible ink on their exposed surfaces, but they presented a dimensional mismatch. The fragments are flat, two-dimensional planes, while the intact scrolls are dense, three-dimensional volumes. To solve this, researchers engineered a geometric bridge. They developed a method to mathematically flatten undulating 3D CT spaces into 2D planes. By forcing a cross-modality alignment between these flattened 3D scans and flat 2D photographs, they could teach an AI to detect a signal that remains completely invisible to the human eye. Developing this alignment pipeline started with the broken fragments. Because their surfaces were exposed, they provided a starting point for capturing a physical baseline. When photographed under 1,000 nanometer infrared light, these fragments yield a highly legible image. The carbon ink absorbs the infrared spectrum differently than the papyrus substrate, producing a stark, high-contrast visual footprint. But the micro-CT scan of that exact same fragment is entirely different. It exists as a noisy 3D voxel grid where the ink completely vanishes. This creates a strict mathematical constraint. It is physically impossible to natively overlay a flat 2D photograph onto a warped, multi-layered 3D coordinate system. Without constructing a shared coordinate space, the high-contrast infrared data is useless for training a machine learning model that must eventually operate inside a 3D CT volume. Bridging this modality gap begins with a computational step known as segmentation. Algorithms trace the papyrus fibers inside the CT volume, extracting a single, warped 3D mesh. A mathematical transformation then unrolls this mesh into a flat 2D plane. The flattening pulls the surrounding 3D voxels with it, snapping them into place. The output is a surface volume. It behaves computationally like a standard 2D image, but it retains multiple channels of physical depth data. This flattening process solves the geometry problem. It creates the shared 2D space necessary to inject human-readable labels into the machine's three-dimensional domain. With the 3D data flattened into a surface volume, the multimodal alignment phase can begin. The 2D infrared photograph is imported directly into this new, flat coordinate space. The infrared image is thresholded to create a strict binary mask. Every pixel containing ink is assigned a value of 1, and every pixel of blank papyrus is assigned a 0. This binary mask now acts as a precise, pixel-for-pixel label overlay resting directly on top of the surface volume CT voxels. By repeating this alignment process across multiple physical fragments, researchers compiled EduScell scrolls, a comprehensive dataset of paired multimodal images. They successfully engineered a supervised training dataset for an invisible signal by hijacking the physical properties of a highly visible signal from an entirely different imaging modality. A flawed neural network might memorize specific pixel coordinates, failing to recognize the actual physical signature of carbon ink. To prevent this, the pipeline uses a strict 8-fold cross-validation setup. The model is trained on one half of a fragment and then forced to predict the presence of ink on a held-out half it has never seen. Under these conditions, the model consistently achieved high precision and recall, scoring a DICE/F1 metric of approximately 0.48 on unseen data. This performance indicates that the model is detecting physical reality. While there is no visual contrast, the carbon ink likely introduces a micromorphological variance in texture or thickness at the 3 to 8 micron scale that the X-rays capture. The strict cross-validation confirms that the model detects an authentic physical signature, verifying that the pipeline is ready to be applied to the intact, unopened scrolls. The proven pipeline shifts away from the exposed fragments and turns toward the massive, fully intact scrolls, containing layers of entirely unknown texts. The segmentation algorithm dives deep into the intact scroll, navigating through ash and debris to isolate the tightly coiled, buried papyrus layers. These hidden layers are extracted and flattened using the exact same mathematical transformation engineered for the fragments. Crucially, these flattened hidden layers lack any ground truth labels. Processing them represents the ultimate blind test of the trained machine learning model. The trained model processes this labelless CT volume, evaluating the voxels and outputting a precise probability map of where ink is located across the flattened plane. The resulting pixel clusters group together with high structural fidelity, matching the specific scale, line spacing, and margins characteristic of authentic Greek writing. This inference yielded the transcription of PHERC 1667, revealing Epicurean and Stoic philosophical texts that have remained sealed and untouched for 2 millennia. This pipeline recovers lost history by engineering a precise geometric bridge between physical modalities, turning previously invisible carbon signatures into verified text.
Scientists are racing to unlock technologies. Breakthroughs in AI are reshaping our future. The future is arriving faster than expected.